All right, well, it's time to start. So last time we were talking about E plus E minus Dijets. And I should have written that. In particular, E plus E minus to Dijets. And we talked about factorization and how to derive it. And I've schematically written the result here. Last time we had a more definite formula with all the arguments made explicit. So there were hard functions, jet functions, and the soft function. And we could either think about measuring invariant masses in two hemispheres and constraining them to be small to know we have dijets, or measuring kind of the sum of the two, which is effectively the thrust. And then we get a slightly simpler formula because we can project these guys down onto guys that only have our functions of one variable. But either way, in either case, we have a factorization theorem that separates the degrees of freedom. And kind of the picture is that we have these kind of scales in the problem. So this is mu jet, mu hard, and mu soft. And we can use this factorization theorem to separate those scales into these functions. And then I started talking about using renormalization group equations in order to sum the logs between these scales. And I want to just finish up that discussion. So for the Wilson coefficient of the operator, or for that matter, for the hard function, which is the square of the Wilson coefficient, you have a very simple renormalization group equation. And that's because momentum conservation is enough to fix all the variables that label collinear fields. So you really just have this overall Q, which is the center of mass energy. And that's the only variable, but it's fixed by kinematics. So there's no convolutions. In the case of these things called jet functions, which we talked a little bit about last time, you end up with something like the Altorelli-Parisi, where there's an integral. It's a little bit different in the sense that we actually know its structure to all orders in perturbation theory. It has this structure. So it only has a very particular dependence on S. It has to scale like 1 over S. So one thing that scales like 1 over S is a delta function or a plus function. And basically, there's only this single type of plus function that can show up. And that's the analog, actually, of something that happened to this guy, where we said there was only a possibility of a single logarithm showing up. OK? So this is how far we got. Whenever you have equations where you have convolutions like this, what you should do is Fourier transform. Because if you Fourier transform something that's a convolution, it becomes a product. So we'll Fourier transform, and in order to be careful about convergence of our Fourier transform, we give it a small imaginary part. And we define a position space, anomalous dimension, as the anomalous dimension up there that depend on S, but now Fourier transformed. And likewise, we define a position space jet function in the same way. And then this formula here, which is a convolution, if you use these in the inverse transforms, you arrive at a very simple formula for the position space. Gamma j. So the Fourier transform of a delta function is just the identity. So there's this term here. There comes that term there. The Fourier transform of a plus function is actually a logarithm. And in order to get that result, you do need to have this convergence, this little I0 in there. So in general, there's a general kind of relation between logs in plus functions like that, and in Fourier space, the kind of highest logarithm you get is L to the k plus 1. OK, so these logs here you're basically, if you think about counting them, you should count this 1 over s as an extra log. And in Fourier space, that becomes explicit. You really just get a log to the k plus 1. All right, but this formula here is something that, again, is of this kind of multiplicative form. So what happens to the enormous dimension in the Fourier space is that it has a multiplicative form. All right, so we have mu d by d mu of j of y comma mu is simply gamma j y comma mu j of y comma mu. So it's no more difficult than this formula up here. Just have to find the right space, which is Fourier space. So then we can make an all-order solution of that formula. Given that we know this, we can just plug in this and integrate. And we've done this a few times now. Let me just do it formally by not doing the integrals, but writing them out in a way that you could do them to show you what the all-order solution would look like. So you can write the solution using this fact and using this fact. So we have to use that fact to convert this logarithm here into something that is just in terms of alphas. But using those two facts, we can do the same kind of things that we've done before and write the all-order solution in the following way. Where the integrals are contained in this w and this k. So here's the non-cusp piece. And then the cusp piece comes with two integrals because it had a logarithm, and we turned one of the logarithms into an integral as well. Hopefully I've gotten all my 2's right. So we saw something similar when we were talking about the running of the Wilson coefficient of the C, because it also had this kind of form with just a logarithm and a constant term. And it's a similar thing here. So this is an all-order solution for the running of the jet function. Of course, we don't know these functions to all orders. We only know them to up to some given order. And so you plug those, whatever order you want to work, you plug it into this formula, and then you can do this integral, and then you figure out these factors here. And those factors are summing the logs. In the case of the jet function, the way that you can think about this picture is that you have to put the guys in the factorization theorem at a common scale. And so one way of thinking about it is as follows. Let's take our hard function and do perturbation theory at mu equals mu h. And then we'll sum logs down to, say, the soft scale. That's one way of doing it. And we'll do perturbation theory for the jet function at a scale mu equals mu j. And then we'll use this renormalization group here, which will just say gamma j. To run this guy down to the soft scale. In that kind of scenario, you wouldn't have to run the soft function. This is like a top-down kind of picture where you're just running the objects at the higher scales down to the lowest scale. That's one way of doing it. You could also do it an equivalent way where you run the saw function, for example, up to the jet scale, and you don't run the jet function. And that'll give you actually the same result. But in the way with the information I presented you, this is the way that you would think about doing the renormalization group, and that would sum up logarithms in the cross-section. And it's very easy if you write it in position space to see what type of logarithms you're summing up. So in position space, if we go back to a formula like the one at the top, basically what happens is that in position space, you again have a product. So these convolutions here, right, which were also of this form, if you Fourier transform, then you end up with a product, d sigma d. So schematically, d sigma dy for, say, where y is the Fourier transform for thrust, would just be h times j in position space times a saw function in position space as well. And there's some q somewhere. But it would be a very simple formula which just has a product. And so you can figure out what logs you're summing. The logs that you're summing, again, just as we talked about before, are simplest to describe when you take the log, because you're really summing logs in an exponent. So if we talk about the log of d sigma dy, then we can enumerate the types of logs that one sums as follows. So these are the leading logs. This is next to leading log, and this is next to next leading log, just like before, okay, when we were talking about enumerating the logs. We talked about before an example where we were enumerating logs in the Wilson coefficient C. Now we're doing it for a full cross-section, but because in position space the cross-section is simply a product of objects, you can think about just, if you take the logarithm, they kind of split apart, and it's very simple to enumerate what corresponds to the things that you would get by putting in anomalous dimensions at a given order. So if you use the leading log anomalous dimension, just the one loop cusp, then you get these terms. You get the higher terms from the running of the coupling. If you put in the next leading log terms, then you get those terms. Okay? And so you supplement that resummation, which comes from this k and this omega in general. You supplement that with sort of fixed order calculations of the h and the j and the s, and that gives you the complete cross-section at some order in resum perturbation theory. So you could do that also in momentum space. And you could write out the formula in momentum space just because, after all, that's what you want in the end. Position space is just really a nice way of deriving the results that then you eventually put back into momentum space in some way or another, because that's where the data is. And let me just show you what the formula would look like, just so you get a kind of picture with all the arguments. So if I were to Fourier transform the resum formula, so here I didn't write the resummation in, right? I didn't write in the evolution factors that correspond to this. So let me do that, but let me do it in momentum space. So I guess I made slightly different choice here. Well, so I'm doing it for the thrust case. These convolutions just mean integrals over the variables that are like this S prime, for example. So this is S prime integral. And this is an L prime integral. This is an L integral. Okay, so there's three integrals in this formula. I guess it's kind of a funny notation, but I could have written integral instead of writing these tensor signs. That would have been probably more clear. Do that. Okay, so there's the formula in momentum space. And it's doing what I said. This factor here is running the hard function down to the soft scale. And this other factor here is running from the jet scale to the soft scale, and I didn't have to run the soft function. I should have written in here that I evaluate this guy at the soft scale. And this guy here, remember, is the non-perturbative guy, which we also talked about a little last time. Okay, so that's kind of the basic structure. These u's, as usual, are summing the logarithms, and then you put fixed order results in for this guy, for that guy, and for this guy here. And in doing so, you get the resummed result. All right. So this fact that I could have done the running differently, that I could have run the soft function, is a kind of consistency. So there are other ways of doing the RG, and they all lead to the same answer. And when I say the same answer, I really mean the same, precisely exactly the same number. So I really mean the same. Not just sort of approximately the same, but exactly the same. And the other ways of doing the RGE are the basic idea of why there are more than one way is, again, this fact that if I do coefficient renormalization, that's the inverse of doing operator renormalization. So there's two ways of thinking about doing the running. You run the operators or you run the coefficients. Okay, in this picture, it's a little bit more complicated because we have three scales. But when I'm running the hard function, I equivalently could have run both the jet and the soft function and not run the hard function. So let me maybe give one other way of doing this just to show you. So I could have run the hard function, say, just down to the jet scale. And then instead of running the jet function, I could have run the soft function up to the jet scale. That would be another way of doing the RG. And that would lead to an equivalent picture. And there's more than that, more than two, because there's three scales in this. There's more than two natural things. There's sort of three possible natural things where you would run to either this scale, or this scale. But at the base of it, it all has to do with this equivalence that we talked about in simpler scenarios earlier. And you can write this also as a relation between anomalous dimensions. So it implies non-trivial things about the formula that have to be true in order for this to work. So, for example, it implies that the coefficients of the cusp anomalous dimension in the various renormalization groups would be in a certain way, that they would be related. And even in the non-cusp anomalous dimensions, which is this formula, there's a relation between the jet, hard, and soft anomalous dimensions. Okay, and that's needed. This is kind of an expression of this fact that you can do the renormalization group by running different objects. So you can derive this formula by just saying mu d by d mu of the cross section is 0. And going through it, if you were to allow, then you would find formulas like this one. Okay. So questions? So I kind of went quick because most of the concepts here are things that we've seen before in simpler guises. The new complication is really that we have this dependence on a variable, which it ended up being y. But by going to Fourier space, it looked just like a simple product again, and y behaved kind of like a simple kinematic variable. At the end of the day, we want to Fourier transform back, but we have a space where things look familiar. Okay.